right, so let's talk about some actual chemistry. Get into some content here. So we're at the beginning of the semester. Want to understand really, ultimately, first off, what is chemistry? So the definition of chemistry, it's a little bit tricky because it's really the study of matter and the changes that matter undergoes and the interaction between matter and energy. So those definitions first really require you to understand what matter is, though. Right? If we want to study matter and how matter behaves, what is matter? So that's really what we have to define before we can fully understand what chemistry is. So matter is defined as anything that has mass and occupies space. And this pen is not working. That is super annoying. Okay. So mass is related to kind of how heavy things are. We'll give a better definition of mass as we go through the semester. Occupying space, we know what that is, just a three-dimensional space. So matter are things that have some heaviness and that take up space. So that kind of seems like everything to me, almost. Is there anything around you that doesn't have some heaviness and doesn't take up any space? So you might think air. Air doesn't seem like it's heavy. Air is heavy. It has mass. It definitely takes up space in the room, but it has mass. If you take a glass container and you use a vacuum to pump all the air out, and then you put that glass container on the balance, it will have a certain mass, right? Because the glass has heaviness, it weighs a certain amount. If then you let air go into the flask and put it back on the balance, it will weigh more. It has more mass. So there is mass in air. It doesn't feel like it to your body because your body is used to that mass, but it does have a certain heaviness, right? That's also, why is the air thicker or there's more oxygen closer to the surface of the earth than there is up in the atmosphere? It's because the air is made out of particles. They have mass. It is matter, and the gravity of the earth pulls it down. So even things that you don't think about as being matter, like air, are still matter. So matter is really almost everything. And if chemistry is the study of matter, then chemistry is the study of almost everything. So is there anything we can think of that's not matter, that is not part of what chemistry is studying? Electricity. So electricity is a form, so something that's not considered matter. We could say energy. So energy is not matter. Electricity is kind of a form of energy. There are lots of different forms of energy. Most forms of energy include, not all, but most include some type of motion. So energy is, you can kind of think of energy as like the movement of matter often. So you can't really have electricity, though, without matter. And since I said that chemistry is the study of matter and how matter and energy interact, energy is still within the area of what chemistry is studying. So that's a good example of something that's not matter, but it's still something that we're going to be very concerned with and we're going to be talking about a lot. Anything else you guys can think of that might not be matter?
Vacuum.
Yeah, emptiness. Nothing. So that's a good one. A vacuum or emptiness or nothing. Yeah, that's nothing. That's good. So we're not going to be studying nothing. We're not going to be studying a vacuum, but we might be thinking about examples where there might be a small amount of matter in a vacuum, or thinking about how that matter might behave in a vacuum. Matter tends to behave differently if there's other matter around it. Particles of matter interact with other particles of matter, and those interactions are important for us to think about. What else? Something that might be a little more abstract. So we mentioned motion. Oh, emotion. Sorry, I didn't hear you correctly. Emotion. Yeah, thoughts. Emotion, ideas. We're not going to be talking about any thoughts or ideas in here. No, so emotion is not really part of chemistry. Yes? Yeah, that's a good one. Time is a concept that is not matter. Although time, according to Einstein, is kind of the warping of space-time. Warping creates gravity, which has a force on matter, so it's not completely unrelated to matter. And when we're looking at experiments, we want to sometimes look at what happens over a period of time when matter, is existing over a period of time. So time is still relevant to us. Yeah, that's good. So you can kind of get a sense that chemistry is pretty much everything, almost everything. And we really want to understand how things behave. We want to break it down and understand what things are made up of. What is matter made up of ultimately, and why do those particles that the matter is made up of behave the way they do? So that's what we're going to mostly talk about this semester. In order to investigate matter and energy and how they interact, and what type of particles exist and why they behave the way they do, we use the scientific method. Right? So in science, we want to understand as much as we can about something, but we have to do it in a careful way so our brains are not tricking us into thinking, making incorrect or unreasonable conclusions. So the scientific method is our guide to hopefully make things as objective as possible and take out any subjectivity that our brains might impart on our ideas. So in the scientific method, we start with making some basic observations, maybe some basic experiments, identifying some patterns or trends, just observing the way things behave around us. And if we take those observations, sometimes we can make a law out of them. A law is usually a mathematical way of describing a trend. So you might look at the ideal gas law, which says the pressure of a gas times the volume of a gas equals the number of moles of gas times the constant R times the temperature of the gas. That's a law because it's just a formula. It's just a way of saying this is how matter behaves. How do we know it behaves that way? Is it some universal truth? No, it's just from observations. We just take a sample of a gas, put it in a container with a certain volume, set it up at a certain temperature, measure the pressure, and we get the pressure every time from that formula. Experimentally, it matches what we observe, matches the formula. So that's really what a law is. It's just a way of describing observations that you make over and over again. Right? You could also think about the law of conservation of mass. Right? That law says you can't destroy or create matter. So if you've got matter, it has a certain mass. And you can move it around from one place to another. You can break it down into smaller pieces or connect the pieces together to make larger pieces maybe. But you can't just take a particle that exists and erase it from existence. And you can't create matter out of nothing. How do we know that you can't do that? Yeah, we've tried it in as many ways as we can think of. Does that mean that we'll never be able to create matter out of nothing? Not really. You might be able to. It's just that we have no idea how, and as far as we know, there's no way to because we've never been able to do it. Right? So a law isn't something that is necessarily always true. It's just that it's always been true so far, so it seems reasonable and reliable to rely on it being true in the future. Okay, so that's what a law is. And so scientists will take laws. A law is really just an observation that you've made over and over again. A law does not explain why. Okay, so that's a key thing. An observation or a law is just what you observe, what seems to be happening. A hypothesis or a theory, those explain why. They are our attempt to answer a question, why is the ideal gas law correct? And so in the ideal gas law it says, if I take a sample of a gas and I put it in a container, I should be able to measure its pressure or predict its pressure based on that formula. And the pressure I predict based on that formula should be the same as the pressure I would measure experimentally. Does that explain why that's the pressure that I measure? No, it just tells me that's what the answer should be. Okay, so once I have a law or an observation, then I develop a hypothesis. I make a bunch of observations. In my mind, I'm saying, okay, this is what I'm observing, but I want to know why I'm observing that. I want to know why when I take a sample of a gas it behaves the way it does and it gives the pressure that it does. So I create a hypothesis. You can't really have a hypothesis without at least some initial observation. So maybe my hypothesis describes something I really can't see. So with a hypothesis or a theory, I have a description or a model that explains something I can't see. Right? So it's hard to know for sure if a hypothesis or theory is correct. All I'm trying to do is to come up with some explanation for why these particles behave the way they do, or some model for their behavior that matches with the experimental observations or the law that I've already come up with that seems to be correct. So for gas, the ideal gas law, I might say, well, the hypothesis is that gas, even though I can't see them, are made up of tiny particles, and those particles are moving around in space and bouncing around off of one another. That's why I observe pressure. Right? So pressure, think about pressure, like if you have a balloon and it's empty, you start blowing up a balloon, it expands, right? That's because the pressure is getting larger the more air I push with my breath into the balloon. The more air I put in there, the more it expands, because the air is made up of these tiny particles and they're moving around. And when they smack and collide on the inside of the balloon, it forces the balloon out. So the pressure is a result of those collisions of the tiny particles inside the balloon. Can I see that happening? Can't really see the tiny particles. I can see the balloon expanding. I can measure the pressure and the volume of the balloon, but I can't see the particle. So the idea that explains the expansion and the increase in pressure is a hypothesis. My hypothesis is that these tiny particles are moving around and colliding on the inside of the balloon. So I can't see that, but it's my hypothesis because it explains what I can see, which is the expansion and the pressure inside of the balloon. So that's a hypothesis. If I want it to become a theory, I've got to experiment with that hypothesis and try to verify it. And I've got to do that in a controlled way. So what does it mean to have a controlled experiment? Yeah, that means you have a comparison. That means you're setting up the experiment so you're testing one variable. one variable at a time. Because if you set up an experiment and you've got all these possible explanations for some observation, the idea with a controlled experiment is to narrow down those explanations to one choice. And in chemistry, that's very difficult because chemicals are made up of tiny particles that you can't see. You're trying to understand how these particles behave, why they behave the way they do, the forces that are acting on them. It's hard to set up an experiment that will allow you to make some conclusion about why they're behaving the way they're behaving. But we have to have controls to let us to do that. So probably one of the most intuitive examples of a controlled experiment is this example here, and it's often used in medicine as an example. If you're giving patients a treatment and you want to know, is that treatment effective, you need a control group and an experimental group, right? So if there's a new drug coming out on the market, they have to do clinical studies before they can release this drug. You can't release a drug unless you've shown that it's at least somewhat effective in some way. So you have volunteers with an illness come in and take this new experimental drug, but you also need a control group of volunteers. They're going to get a placebo. And then you can compare. Every detail of the two control groups is exactly the same except one group. The only difference is one group gets the drug and the other group gets a placebo. You've isolated all the other variables. The only difference or variable left is that one group gets a drug and the other group gets a placebo. Then if there's a difference in the outcome of the two groups, you have some idea that the difference is because of the difference that that drug was actually making for the experimental group. It's hard to control all the variables though. What if one group has some patients that are elderly and the other group had patients that are younger? That's not going to be a good comparison, because if one group does a lot better health-wise, it might be because they were younger. It might not be because of the drug. Or it might be a lifestyle difference. Maybe one group has a healthier diet than the other group and they do better, and you start to think it's because of the drug when it really wasn't. So in medicine and in chemistry, it's really hard to control variables. It's really hard to say for sure that an observation you make is due to a certain hypothesis being correct. So you need to do lots of repetition. For a hypothesis, which is basically just an off-the-cuff explanation for some observation, for that guess or idea to become a theory, which is basically a scientific fact, you need lots of repetition, lots of variety of experiments that are effectively controlled, so you can say with a great deal of confidence that this hypothesis is now a theory. It's now something that we believe to be true because we've done lots of experiments, and this idea that explains the behavior of these particles, or this idea that a drug is effective, has been shown to be true through lots of repeated controlled experiments. Any questions about that?
Yeah. What's the difference between law and theory? Are they the same thing?
No, a law is an observation, something you can see or measure directly. So the ideal gas law, you can measure the behavior of a gas, you can measure its pressure directly. A theory is an explanation for that behavior that's backed up with lots of experimentation.
Theory leads to law eventually.
Actually, it's actually a law that leads to a hypothesis that leads to a theory.
Okay.
Because a law is something that you can directly observe. A theory and a hypothesis is something that explains that observation. So I can directly observe the behavior of a gas. I can put a gas in a container, I can get a pressure sensor, I can measure its pressure. I can do this experiment lots of times and develop a law from these direct observations and experiments. The theory then comes later, and the theory says, why does the gas pressure increase when I put more gas inside the vessel? Right? The law is just saying the pressure increases when I put more gas inside this vessel. That's a direct observation. I put the gas in, I measure the pressure increase, I can measure that directly. That's my law. The theory is, why does the pressure increase when I put more gas? And so that's called the kinetic molecular theory, and that theory says that because the gas is made of tiny particles that are moving around, I can't see that, so it's not a direct observation. It's not a law to say that there are tiny particles that move around to create that pressure. That's a theory because it's an explanation for the observation. So the theory is that there are tiny particles, they move around, the collisions that they create inside this vessel is what causes the pressure to increase. So when I put more of them in, I have more collisions and the pressure goes up. So that's a theory because it matches with all the experimental observations, but it's not something I see directly. It's an idea I have that explains the law or observation that I made.
You're mentioning the experiment, one group gets the drug, the other gets the, what was that you said?
Control? Oh, placebo.
Placebo.
Yeah, placebo is just like a sugar pill.
Okay.
So it's not actually a drug or medicine, but you give it to patients so that they don't know if they're actually getting the drug or not.
Oh.
Because if you gave the experimental group of patients a drug, and then you gave the other group of patients nothing, they would know they're not getting the drug, and then mentally the likelihood of them getting better would be less because they would be like, well, I'm not getting anything. I don't expect my condition to improve. When patients get a placebo, sometimes they get better or have less symptoms simply because of the mental idea that they think they might be getting something. So for a drug to be really shown effective, it needs to be better than a placebo. Any other questions about scientific method? Okay, so let's just do a little practice here with these text examples. Make sure that we have a good idea of how to distinguish between a law, a hypothesis, and a theory. So let me get to the right page. 1.4b. So we want to classify the statement as a hypothesis, law, or theory. And the statement is, an autumn leaf gravitates toward the ground because there is an attractive force between the leaf and the earth. So how would you classify that statement? So in this type of question, when you're trying to distinguish between a law, theory, or a hypothesis, the first question you want to ask is this a direct observation or is it an explanation for an observation? Does it invoke something I can't see directly? If I can see it and observe it directly, it should be a law. If it invokes an idea that I can't see or observe directly that explains an observation, then it's either a theory or a hypothesis depending on how much experimental evidence there is for it. So in this particular one, it says, autumn leaf gravitates toward the ground. If that were the end, then I could say it's a law. Right? A law would be things fall down. They don't fall up. But it doesn't just say that. It says an autumn leaf gravitates toward the ground because there is an attractive force between the leaf and the earth. Can I see the attractive force between the leaf and the earth? No. It's not a law. It's not a direct observation because I'm invoking an idea that I can't see directly, an explanation for the leaf falling. And that's gravity, right? So is gravity a hypothesis or a theory? It's a theory, right? Because we've done lots of experiments with gravity. We understand it mathematically in a lot of detail, and that theory has never been incorrect. But it's still a theory because I can't see it or observe it directly, and it's an explanation for something I can't observe.
They did discover gravitational waves.
Yeah, they did discover some evidence, for gravitational waves. Yeah, so that also, it's a good point to make about whether seeing something directly or whether seeing something with an experimental device like a spectrometer or something, which of those actually is considered direct observation. There's some gray area there. I would agree with that. So the theory of gravity, in that it's called a theory, calling it a theory doesn't mean you don't have much confidence in it. It means you have a lot of confidence in it. And the fact that they can observe some gravitational waves just gives you more confidence in that theory, especially in Einstein's description of gravity, which is superior to Newton's description of gravity. For 1.4c, all matter is composed of very small particles. Is that something you can see directly?
No.
No, you can actually, given the right instrumentation, observe single atoms. But you can't observe necessarily the particles that make up an atom. You can't see an individual electron or the other particles inside the nucleus of an atom. You can't see those directly. So that is not something that is a law. It's not a law to say that atoms or that matter is made up of tiny particles. It's a theory. It's still a fact, because we've done so many experiments that allow us to observe the behavior of those particles and phenomena that are strongly suggestive that there are tiny particles that make up matter. So it's not a hypothesis; it's a well-proven idea, but it's still an explanation for direct observation rather than a direct observation in itself. So that makes it a theory.
So the modern technology cannot help us to see the neutrons and electrons?
So technology helps us see those particles, but we don't see them directly. Yeah, right.
With the naked eye.
Yeah, we can make the
Yeah, you also don't really see them with a microscope. You know, you see the effect that they may have colliding with something else, or they may interact with some fluorescent material that causes light to be emitted, or they're interacting with light, or interacting between one charged particle and another charged particle, and you can see the electrical effect of that interaction in some way. So there's lots of tricks that scientists can use to detect the presence of those particles without seeing them directly. And that's evidence for the existence of those particles. It's evidence for the existence of atoms and atomic theory. 1.5. The force acting on an object is equal to its mass times its acceleration. That is a law, right? Right, that's a mathematical way of describing something you can observe and measure. The universe as we know it started with the Big Bang. That is a theory, right? So it's based on the idea that we continue to see the universe expanding. So at some point the universe must have been much smaller, and it must have started at some point expanding, and we have that background radiation that we can see as well. It's evidence for that. Evidence for the Big Bang is not nearly as strong as it is for some other theories, right? So not all theories are equal. There's a lot of nuance there, and you have to look at how much evidence there is. Then 1.5c says there are many civilizations more advanced than ours on other planets. That is it's a hypothesis, right? So it's not unreasonable to think there might be, but there's no evidence for it. So we would have to reach a point where we could experimentally test that before it could become a theory. At this point, it's just a hypothesis.
We don't even have a chance to observe it.
Not yet. So at this point, there's no way it can become a theory. We would have to advance our technology a lot more.